All right, we're going to do Inorder, Successor, and a BST. So they give us the root of the tree, and they give us some node P, and we just want to find the successor of P, which is just the smallest value, which is greater than P. So we'll do this two ways. The first way we're going to do it recursively, then we'll do it iteratively. So recursively, what's our base case? So if the root is null, then just return null. And if the value of the root is less than or equal to P's value, well, if this is smaller than P, because less than or equal, or it's smaller or equal to P, and we're trying to find a value that is greater than P, we want to find the smallest value that is greater than P. Well, we need to recurse towards the right side, right? Because in a binary search tree, the smaller values are towards the left and the bigger values are towards the right. So we're going to go further to the right side. Let me copy paste that. And we're going to just recurse towards the right side. And this P here is never going to change. We're going to keep passing in P. The only thing that's going to change is whether we're going towards the right or towards the left. Okay. Now, if we've gotten this far, oh, actually, this should be returning. So we're going to return whatever we find on the right side that is greater than P. But anyway, so after we get past this, if we get past this condition and we're down here, then that means that root value is actually greater than P. Now that means that root is the potential successor of P. We don't know for sure yet because there could be some value that is smaller than this root's value, but is still greater than P. So here's what we're going to do. We're going to recurse towards the left side. So tree node left equals, let's just copy paste this. We're going to change this to left. So now we recurse towards the left side. And now we're going to return if left is null. Actually, let's do this. If left isn't null, return left. Otherwise, return the root. And why does this work? So if we recurse towards the left and we find a value that is less or that is greater than P, then this value must be less than the root's value. Therefore, we have to return left. I'm going to say that one more time. So if we found something, so when we recurse towards the left side, if we found a node that is greater than P, because we went left, that means that this value, this root.left, it must be less than root.val. So that's why we're going to return left here if we found anything. And if we didn't find anything, well then root must be the successor. Because root was, if we got this far, remember if we got this far, this means that root.val is greater than P. All right, so let's do the iterative solution now. Let's just comment this out, copy in a signature. And all right, so for the iterative solution, our algorithm is basically the same thing. We're just going to iterate down our tree, and we're going to step towards the right or we're going to step towards the left, depending on whether the value that we're currently at is less than or equal to P or greater than P. And we're just going to keep track of the minimum value that we find along the way that is greater than P. So let's create a temporary or a variable to iterate down our tree. So we'll just call it current or cur and set it to root. And we're going to keep track of the minimum value that we find that is greater than P. So we'll just set this to null for now because we haven't found anything yet. And while current is not equal to null, we're going to say if current.value is less than or equal to P's value. So if this value is less than P, or less than or equal to P, that means we need to step towards our right because we're looking for values that are greater than P. So, or not current.right. Current equals current.right. Okay. And if we find a value, so this means, if we hit this else statement, that means current.value is actually greater than P's value, which is good. That's what we're looking for. We're going to go ahead and set min equal to current because this node is greater than P. Right? Okay. And we're going to say current equals cur.left because if this value is greater than P, we now need to look for smaller values or values that are smaller than this current, but that are still greater than this P. So we want to step to our left. And if we, so let's say we set, so cur equals cur.left, we're going to step to our left. And when we go through this iteration again, if we hit this again, that means that because we stepped to our left, that this new cur must be smaller than the last min that we encountered. So we're going to go ahead and set min equal to that current. And again, we're going to try stepping to our left again. And again, this whenever we go inside here, this also means that current.value is greater than p's value, which is good because we're looking for values that are greater than p. But anyway, like hopefully you can see this, that because we're stepping to our left because it's a binary tree, that means we're going towards smaller values. And every time we go in here, that means we've encountered a smaller value that is still greater than p. Because if it was less than or equal to p, we would have gone in here. All right, and then all we have to do is return min at the end, because this represents the smallest value we encountered that is greater than p. Let's just run this and submit. Cool. So that's the iterative solution. So this would be O of one space compared to the recursive way, which would be O of h space, where h is the height of the tree. Time complexity for both of them would be log of, I want to say log n, but if this binary search tree is actually like a linked list, then it could be, I guess worst case could be O of n. So it could be, I guess the worst case is O of the height. Yeah. So in the worst case for both of these, and for the time complexity, yeah, it would be O of the height of the tree. Okay. So that's pretty much everything for this question. If you have any questions, you can leave a comment, and you can like, subscribe, whatever. All right, bye.